properties with particle size. Okay, and coming to the next one is magnetic materials. Okay, so that means if you take bulk, you have many grains, and if you have grains, you have the possibility of magnetic movements will align in different directions. So you will have multi-volt, right? You have domains, multi-domains you will have in your material. When I'm decreasing the particle size, see, when I'm going down, nanoparticle radius, I'm decreasing. What will happen? I'm reducing the number of domains, and I can attain a single domain region. And after that, few materials will show like a super paramagnetism. Like the best example, if you take iron oxide, Fu2O3, so at room temperature, it is ferromagnetic in nature, and if you go down and make with around below 50 nanometers, it will show super paramagnetism. That means the magnetic properties can also be influenced with the decreasing of particle size. That means few materials which are not magnetic at bulk will show very strong magnetic orderings. So when they go to nanoform, so that's why you can improve even magnetic properties also. And another interesting one is the electrical properties. Like you can see this from band diagram, and there are many BTech students. You all might have know the band diagram, right? The valency band and conduction band. You might have studied in your engineering physics. So if you take metal, bulk metal, what will happen? Your valency band will overlap with the conduction band, and because of that, you are getting good electrical conductivity because the electrons are available in the conduction band at room temperature itself, so it will show very good conductivity. So but what will happen when you are decreasing the particle size? So what will happen, this so you all might have some idea, right? Conduction band, it is not a continuous band, it is also having discrete energy levels which are very closely spaced. As they are very closely spaced, we will see this like a band, but it will have many energy levels which are close to each other. So what will happen when you are decreasing the particle size? So these bands will move away from each other. So you will have, like when you are moving away, you see I'm decreasing the particle size from here to here, and you can see the energy levels are moving apart and the band gap is increasing. So that means what will happen? So when you are having a metallic nature at the bulk form, and the same metal will behave like an insulator. It will become like an insulator when you decrease the particle size. So that means you can tune the electrical properties of the materials, so by manipulating the particle size. So that means this slide clearly shows you how the nanomaterials are different from bulk, and why we need to go for nanomaterials in spite we are having very good number of bulk materials naturally available in the universe. Okay, so all the properties, not a few things I mentioned here, many properties, like if you take the mechanical properties, so it will be enhanced like thousands of times when you move to nano. So there are many advantages, like when you are moving to nano. Okay, and after knowing these things, how to characterize them, you will come to know, because you all might have some idea how to prepare nanomaterials, because many speakers have delivered many lectures how to synthesize nanomaterials with the different techniques. There are many techniques are there, top down, bottom up. So in top down, you will have many chemical synthesis like colloidal or sol gel, hydrothermal. Many routes are there when you see the top down. So it is nothing but you will take bulk material and you will heat that, or you will crush that and make that into nano. So generally ball milling, high energy ball milling will come under so top down techniques. So once after synthesizing those materials, what we need to do, we need to characterize them. We should know whether you got the expected material or not, the nano form or not, and whether you got that, if you get that material, will it have any defects, or will it have any strains present in that, or is there any impurities? So these things you will come to know when you characterize them with the proper tools. Okay, and you might have got some idea from the before lectures, like there is a preliminary characterization we'll do with the powder X-ray diffraction technique, which gives some idea whether you got the material with proper crystal structure or not. But in support to the powdered X-ray diffraction, there are many powerful techniques are there. So which is among this microscopic tool. So transmission electron microscope is one of the best technique which will give the support, very good support to your powder diffraction data, powder X-ray diffraction data. So we'll quickly see how it will support your powder diffraction data. So with small example. Okay. And what is this technique, transmission electron microscopy? What it means actually, this you will use very high energy electron beam. You all know, right? When electron is moving, so it will behave like a wave from your quantum mechanics, de Broglie hypothesis. Same way, your electron will be here accelerated with the very high potential. You can see at 100 to 300 kilovolts potential gradient you will apply, and these electrons will move with very high velocity, and then they will pass through your material. That means the one which you want to characterize, you will keep. So in the specimen holder, like here I'm showing, typical TEM instrument will look like this one. On top you will have electron gun, and here you will have some lenses system, and here you are seeing here one chamber. In through this chamber you will introduce your sample into the path of the electron beam, and there are some optical systems will be there, so which will control the flow of electron and which will focus the electron beam to a desired points. Okay. And whatever the thing that is happening there, you can see here you have small microscope and you have fluorescent screen. So on that you can see what is happening when they are falling on that. That means you can do parallelly, you can do imaging, and you can also do electron diffraction. Okay, so we'll see that how the results will look like. And what will happen, this technique gives the images of internal structures, and for that what the main thing is, your sample should be very thin. So let me take, you take very bulk material, like you take normal, like copper, like foil, very thin foil, and if you put in the beam, in the electron beam, you cannot get the electron diffraction, you cannot image that particular sample. So that means what you need to do, you need to do a lot of like processing to make the sample itself. So that is the main difficulty of using this transmission electron microscopy. You have to make the sample very thin, then only your electrons will pass through your material. Okay, otherwise electrons will not pass through your material, and you will ended up with very poor resolution images. Okay, so that is a one difficulty in doing this experiment. Okay. And if you see, there are many techniques are there in when you are imaging the process there, but we'll have mainly two things: one bright field image and dark field. So, and the main difference is which beam you will pass through your objective, like object aperture. Okay, so if you are passing a diffracted beam through the aperture, we call that as a dark field, and if you're using the direct beam, you call that as a bright field. Okay, so don't worry about these things, theoretical things, and we'll see. So generally we go with the dark field imaging, and which will give very good contrast images. Okay, so let me quickly show. So what generally we do, like after preparing nanomaterials, right? We all take a TEM images or SEM images, or we'll characterize with some other techniques. Okay. So general thing what we do from by using the TEM is we'll see the morphology, right? You prepared materials, and you when you're preparing you from your synthesis protocol, you will expect that you will get nanospheres or nano or diamonds, or you may get nanoflakes. You will expect some morphology as per your synthesis protocol, and you will cross check that by seeing or by imaging them directly, whether you got the expected morphology or not. And another thing is you will see the structure. How we can see the structure from a TEM? You can see here morphology, like the same silver nanoparticles by following different synthesis protocols. You see the same silver nanoparticles we can prepare as spheres, and it's a mixture of spheres, and you are seeing some triangular like pyramids, and you are having rod kind of shape, and you are having wires, silver nanowires or nanofibers, and you are having cubes, again pyramids, needle kind of thing, and this dendrites. So it means the same silver nanoparticles you can make with the different morphologies, okay, just by tuning your synthesis protocol. Whether you change the pH value or you change the whatever the initial reagents, or by changing the solvent, so you can get, or you can tune the morphology of the silver nanoparticles. And again the question is why we want to tune this morphology. The problem, again answer is same. When you are tuning the morphology, you are trying to increase the surface area of the particles, okay. And you see, compared to this nanospheres, this nanofibers will have large surface area, okay. So when they are having large surface area, so automatically more catalytic reactions will happen on the surface of those silver nanofibers. So that is the one thing. Only thing is, when you are moving to nano, you are trying to increase the surface to volume ratio, and for that you can also play with the morphology. This is one of the best example. And TM is a very powerful technique. You can show them, show the reviewer how good your particles are, okay, in terms of morphology. And the next one you will do is you will try to corroborate your powder extra diffraction data. You all might have seen this data in the previous presentations. This is a powder diffraction data, and which will typically show the intensity versus your diffraction angle. So, and these reflections are like characteristics for a given material. They are like fingerprints, we can say, for a given materials. Okay. So this is the silver nanoparticle, the first one, and this one is gold nanoparticles, and they are the corresponding images. I mean, powdered diffraction data. In support to that, so what we have done the electron diffraction. That means your TEM is useful not just for seeing the particles, or not for the imaging purpose. You can also do diffraction property. That means here you are using X-rays for the diffraction process. Here you are using electron beam for the diffraction. So you all know, right, when electron is in motion, it will attain wavelength, and as that wavelength is matching with the, in general, the despacing of the crystals, you can also see the diffraction with the help of electron beam. Okay. You might have studied the famous experiment, proving the particle, I mean, wave nature of matter. Okay, Davis and Germer experiment. Similar thing, electron a beam will behave like a wave, and which will show diffraction from the crystals. And this each diffraction ring corresponding to, it is coming from a set of reflections. We call that one as plane. And you see this plane 111 is exactly matching with this 111 and 200. We call them as HKL values, and they are matching. That means this TEM is not just for imaging purpose. You can do the electron diffraction, and you can support your powder X-ray diffraction data with the electron diffraction images. So because of that, this TEM is very powerful technique compared to scanning electron microscope. And coming to that, is that enough, like using TEM for morphology and knowing the structure? So it's not that. So you can study many things. Okay, we should not stop our studies there. It depends on which materials you are characterizing. As I mentioned, I'm going to focus more on 2D materials, especially graphene and chalcogenides. So where they are getting main attention in the electronic devices. Okay, here STM is it's not something different technique. It is also TEM. So that is scanning transmission electron microscope. And you can see here graphene, you all know, right? Graphene, you have graphite, many layers, and you remove one layer from the graphite, and we call that one layer is graphene. Okay. And if you have graphene, see graphene, you have so hexagons with the carbon, right? So, and if you take the STM image, I mean, scanning transmission electron microscope, then you can see how accurately it is showing the symmetry, right? So all these are in 5 angstrom scale. If you see how they are maintaining this is the simulated structure from the software, and it is clearly depicting in your TEM image. That means you're not just seeing the morphology, you can directly see the atoms. If you have very powerful TEM, you can go up to angstrom range and you can see even the atoms, how the atoms are arranged in your material. Okay, so like another best example is MOS2. This is also layered 2D materials, and so you can see how they are clearly showing the atom by atom picture. That means when you are using TEM in the next time, not just stop your studies up to morphology and crystal structure, you go a little bit deep and you understand how the atoms also arranged. That means what information you can get from this atomic structure is you will come to know in one or two things. Okay, and coming to misalignment, another one. So like you have a single crystal, right? This also, and the top images will show the theoretically developed images and the corresponding diffraction patterns. If you see single crystal means it will not have any grains or grain boundaries. Only one grain will present. That means your long range order will be there, and there is no any discontinuity in that. And if you see the diffraction pattern, it's very clear pattern, right? The spot pattern. Each point here represents one set of planes in your X-ray diffraction. Okay, and we call this one as a reciprocal space. And now what will happen if you have multiple grains? That means instead of single crystal, if you have polycrystals, then what will happen? Let me take the best two simple thing. I have two grains. We call, when you have polycrystalline, we have grains. We call this one as grain and this one as second grain. And let us say they are tilted with some angle theta. We don't know that how much angle, but you can get practically with the help of transmission electron microscope. That means if you do TEM, so that means corresponding to this grain, you will have a set of reflections. Okay, this we call it as electron diffraction, selected area diffraction. So, and corresponding to this grain will also project some diffracted images. And now as this grain is tilted with this grain with some angle, with same angle you will see these diffraction spots also will be tilted. So this is so powerful. That means even if the small misalignment in the atoms, so it will be reflected in your electron diffraction pattern or direct imaging of atoms. Okay. And coming to the next one is grain boundaries. So as I mentioned here, you see the graphene, because the graphene is here. So that means you are having graphene, and then you see this graphene is not having any impurities. You see very proper alignment of these hexagons, right? All are perfect. There is no any discontinuity, or there is no any defect, or there is no any problem with this image. That means that it is representing that your graphene is high pure. Okay, whereas if you see this one, you are having some joint right here. It is showing just, that means you are having one grain here and another grain of graphene here, and both are overlapping. So that means you are having grain boundary which is separating these two grains, so which is clearly reflecting in here. But when you do the similar, and like X-ray diffraction, you cannot get this kind of information from XRD. Okay, further you need to do TEM, and that to high resolution TEM. If you do, you can see how the atoms are arranged so in your material, and if any small misalignment is there, that can also be seen here. And even you see, if you are clearly zooming that, you can understand from this. So that means when they are sharing, that means when two grains are coming close, there is a possibility that distortion will come in the hexagons rings. Okay, and because of that you are having some defects, like you are having arrangement of hexagon pentagon hexagon pentagon, and you can get the how much angle that both the grains are tilted with each other, and you got around roughly 27. Okay, there are some different softwares are there to analyze this data, but first getting this data is very important. For that you need to have very good samples and very high-end TEM, then only you can get these kind of images. Okay, and the next one is So twin boundaries, this is very important in the case of like those, if any mechanical students are there. So if you are making like any alloys, okay, there is a lot of possibility that you will end up with twin boundaries or tilt boundaries, or many kinds of we cannot say this is as a defect, but so twin boundaries and tilt boundaries and grind boundaries, these are like different things that will happen when you're processing your, or when you're preparing your alloys. Okay, and you see here also you are seeing atom by atom. You please look into the picture clearly. So, and this is the real not this image was collected with a little bit lower magnification. This is with the higher magnification, like 2 nanometer magnification. And when you are applying the strain to this one, see your grains boundaries are tilting with some angle. Okay, so this twin boundaries is nothing but, you all know, right? Twins, that means you have similar things. Okay, like twin sisters or twin brothers mean they have the similar, they look similar. A similar way here, in this boundaries, if you see this boundary and this one, okay, and they both look like mirror images. That means if I keep one mirror here, okay, so the one which is present here will turn out to be here. That means one side of the grain is, or boundary is, just a mirror image of another one. Such kind of boundaries we call it as twin boundaries. And those things also, you see it clearly seeing directly from your eyes. There is no any different technique here. There is no any other things are involving. Whatever the atoms that are arranged, you are directly seeing with the help of this transmission electron microscopes. That's why this is very powerful technique. So in understanding the in-depth crystal structure or defects or strains present in your nanomaterials. Okay, so another interesting thing is, I think many of us also doing research in amorphous materials like glasses or something else. Okay, like you all know, right? Silica. You can get the silica in crystalline form or in amorphous form. And so, is this technique like TEM is useful to understand or probe the amorphous materials? So obviously you can do that, because you see this is a developed model, and this is also model for amorphous. You all know, right? Amorphous and crystalline. Crystalline means regular and periodic arrangement will be there. That is what you are seeing in this model. And whereas in this atoms, I mean silicon, again, silica composition will not change. But what will happen? How they arrange those molecules, right? That will change. If this is a random arrangement of atoms, and that gives you amorphous. You have, there is no long range order here, and long range order will present in this. Same thing if you see through TEM, you see how corresponding to this, you are having very good TEM images that are showing the long range order present in this. Okay, and whereas if you see this one, you are seeing again such kind of ring patterns, but they are not regular. I mean, they are not arranged. There is no periodicity and there is no long range order. So that's why we can say that this is amorphous in nature and this is crystalline in nature. That means, so just by seeing the TEM image and understanding whether periodicity is present or there, so you can get whether the material is amorphous or not. If it is amorphous, you are getting directly from the what is that? XRD. But in support to that, so let us say if you are collecting your powder diffraction data by placing your sample on a glass plate. So there is a possibility that when they are collecting the X-ray diffraction, instead of getting the data from the sample, so you may ended up with the data will coming from the glass plate. So because the glass plate is amorphous, you will end up with amorphous nature in the powder XRD. So that's why, so presenting only the powder XRD is not sufficient for moving to, if you want to keep your paper in the high quality journals. In support to that, if you keep any TEM images showing that they are amorphous in nature, and that can also be reflected in the diffraction. You please, the difference between these two, this is imaging. TEM imaging, and with the help of TEM, you are doing the diffraction experiment, electron diffraction. So if you have crystalline sample, you will have well-defined points or rings at least. Okay. So whereas if you have amorphous, you will have diffused rings. So that means you see it's not well defined rings, they are diffused rings. Okay, so that can also confirm that your sample is amorphous in nature. Okay, so that means these are the few things which you can get from your TEM images. Not only this, you have many more things you can get from just by taking very high quality TEM images. You can get many either defects or tilt boundaries or twin boundaries or any misalignment. You have graphene, right? There is a many things like instead of single layer graphene, if you have another graphene layer, they'll put on the top of that and they will tilt with some angle, and that tilted, that because of that tilting you can probe magnetism in the graphene. So in order to show how much angle that tilted, and to confirm that, you need to show your TEM results with for the supporting. Okay, in those conditions your TEM is very powerful, but only one problem with the TEM is you need to prepare your sample properly. Okay, so if you are using a solid sample, like you should make as thin as possible, as I mentioned, less than 1000 angstroms. And if you are using nanoparticle, that is fine, you can do all these measurements directly. Okay, and these are the things about TEM. And then we go for probing the nanomaterials with the spectroscopic tools. That means now you have idea how to prepare the nanomaterial from your previous talks, and then how to characterize them. That means internally how to see the structure and how to image them, and how to corroborate your PX powder XRD data with the TEM. So now you prepare, let us say you are preparing one Li with some 30-40 composition. Okay, A and B is the two elements present, and you want A 30% and B 70%. And you prepared your synthesis protocol in that way, and you ended up with material and it is showing the pure phase and everything. But how you know that it is having that A is having 30% and B is having 70%? Because that percentage of those elements is also very crucial, and because of that your complete properties will change. Okay, that means when you prepare nanomaterials, understanding the composition of that compound is very important. And generally we use SEM edex, and but which is not useful much when you're using for nanomaterials. So that's why most of the people recommend this technique, like induction coupled plasma, that is what I mentioned, right? ICP, and atomic emission spectroscopy. That means we use very simple concept, like you take atom and you give energy. What will happen? Electron will go to excited state, and when they come down they release energy which is equal to the separation between the energy levels. So that means that energy will be emitted in the form of wavelength, right? And that wavelength will give complete information about what element is present in your sample. That means by using very fundamental thing, absorption and emission, you can get how much percentage of atom is present in your sample. Okay, so information about the whole sample, because so when you are doing this ICP, what you do is you will dissolve your sample in a solvent. Okay, that means you are getting the information from whole sample. Whereas when you are doing SEM edex, right, or you will put one point at some region in the view, and from that you will collect the edex. That means whatever the information that you are collecting from edex, it's very local, and you cannot generalize that for the whole sample. That is one disadvantage with the SEM edex. Whereas this ICPA is what you do, you take, let us say, 1 mg or 2 mg of sample, and you will dissolve that in your one of the solvent, depends on your sample. That means you are getting information about whole 1 mg or 2 mg, that means whole sample. That means if you take homogeneity, like whatever the values that you will end up with, the ICPIS are more accurate compared to SEM edex. Okay, sometimes whatever the SEM edex will match with the AES, but still ICP-AES is more preferable compared to SEM edex, because it gives the information about whole sample, not the local. And how the pictorial, just how the instrument will look like, this one. And this is the real instrument. So And you will dissolve your sample in some solution, and that you will keep, and it will be taken through pump to a nebulizer. What in nebulizer, what will you do is you will send argon from one side, and you will have the nanoparticle. This liquid will go in this, and it will be evaporated here. This nebulizer, what it will do, it will make aerosols. Maybe your mixture of your argon and your nanoparticles, and that aerosols will be sent through this torch. And here you have RF coil. So what this will do is, it will you will send very high power, so that it will generate plasma. Okay, that means when these aerosols are entering through the plasma, what will happen? It is gaining energy, and as nanoparticles will having different atoms, right? And the electrons in atoms will excite to the excited state, and they come back when they are coming out of this, and they will release energy in the form of wavelength. And you will put some optics here and some processing units to collect the data. That means if you see your ICP data, you will get intensity versus wavelength. That means the wavelength, the position of this peak gives the information about what atom is present in your sample, and this intensity of this peak will gives the information how much percentage of that particular atom is present in your sample. Okay, so that means, so as this wavelength is the characteristic, the fingerprints for given wavelength. Let us say if you take copper, so when you excite and de-excite, it will emit some wavelength. So when you take other element, you excite and de-excite, it will give other element, right? Other wavelength. They never coincide with each other, but there is some possibility. So that is the different part. Okay, but in general, these wavelengths are characteristics or the fingerprints for given, selected atoms. Okay, so that's why whatever the information you will get is more accurate and more uniform. Okay, and just me present one result, prepared the composite like PTNI, platinum and nickel nanocatalyst they prepared. So and they put this on RGO, reduced graphene oxide, and they have done TM, EDAX and ICP. Here the results are, you can see the PT-NI ratio they have done with EDAX and ICP AES. Okay, you see both the things are matching with the expected composition or ratio, but still what I suggest is doing ICP is more preferable, because when you present your results, only EDX results in your paper, and if you are showing very good properties, enhancement in properties, surely the reviewer will ask, so please support your EDX data with ICP data, because ICP is more accurate and more uniform, because it gives about whole sample, not a specific point. Okay, so that is the information you can get from ICP AES. You are using a spectroscopic technique to get what elements and how much composition is present in your prepared sample, which is very important. So the next one is, and before going to that, there are some precautions are there, as I mentioned. So you have to solve your sample on a solution, right? So that means your solubility should be very good. If your sample is not properly soluble, so then what will happen? The particles will disperse in that solution, and when you are sending through nebulizer, and it will disturb the process of excitation and de-excitation. So that's why, so it should be very you should check for the solubility. Okay, I mean your sample should be soluble in your solvent. That means you have to find the right solvent for your sample. And the next one is, you all know, right, when you are preparing nanomaterials, you will use different organic solvents, and those will also hinder this emission and absorption process. So that's why you need to clean your sample thoroughly. That means before doing this ICP, and you have to remove these organic solvents. Just what, by doing different purification processes, or you can heat the sample at around 60 or 70 for a couple of hours, because generally all organic solvents will evaporate in the range of 70 to 80. So such that you can remove organic solvents from the nanoparticles before going for ICP and AES measurements. Okay. And another problem here is, as even though I mentioned these wavelengths of fingerprints for a given atom,
there is a possibility like if you are having just side by side atoms, okay, two, if in a periodic table you have two atoms which are side by side, and there are possibility that their wavelengths will overlap. Okay, they may not overlap exactly, there's a small difference, let us say small difference is there, then you can choose a different wavelength for atoms. Let us say one wavelength is match, a atom is matching with another, I mean uh, wavelength of b atom, then you can choose a different wavelengths for two different atoms. There is a provision to select wavelength when you are doing that experiment, so that also be taken care when you are giving the wavelengths, feeding the wavelengths to the system, it should be taken care. Okay, so if you take all these precautions, you will end up with very good results. Okay, and in comparison with SEM EDAX. Okay, by knowing the composition, then another important and powerful technique is Raman spectroscopy, and this is quite useful in characterizing materials, especially nanomaterials and carbon-based materials, and that's why I'm showing results based on carbon-based materials. Okay, it is also a spectroscopic tool, and how the technique will work, it's a scattering, because you take some laser light and you incident on material. So what will happen, the scattering will happen, so inelastic scattering, and this has happened because of phonons present in your sample. Okay, that means it's just a scattering of incident light by phonons present in your sample. Okay, and why this is so important or powerful is this technique is very sensitive. That means if you have very small impurities, and you can get the local information, if any small strain is present in your sample in the atomic level, that also can be probed with the help of Raman spectroscopy. And another important thing is it is non-destructive. That means it will not damage your sample unless if you are using like polymers and very high energy laser beams. Then there is a possibility that the sample get damaged. But in general, so Raman spectroscopy is a non-destructive technique. Okay, and coming to the, because the it's very important Raman spectroscopy when you are doing carbon nanostructures. So when I say carbon nanostructures, you have many types like zero dimension, one, two, three dimension. Like the thing is when you have carbon, right, sp2 and sp3 hybridization, and that small, I mean, a change in the hybridization sp2 to sp3 can also be probed with the help of Raman spectroscopy. So that's why those who are working in carbon nanostructures like carbon nanotubes or graphene or fullerenes, they will support their results with Raman spectroscopy. Okay. So now let us take one case study like graphene and how you can use Raman spectroscopy to understand the graphene. Okay. And if you take graphene, you all know, right? Graphene is nothing but layered, single layer. Like you take graphite, you know, right? Poly, I mean hexagons, carbon hexagons, and they have uh, like layers, many layers. Okay, that means from that, if you peel out one layer, and that one layer of carbon atoms, we call it as graphene. Okay, and the pictorial representation is shown here. And if you collect the Raman spectroscopy or Raman spectra of that graphene, you will end up with this result. So this is the result of a pure graphene. Okay, that means if you take pure graphene, it will have two characteristics peak. One is the G band, another one is 2D band. Okay, and this G band we call it as it is coming because of the stretching of CC bond, and whereas 2D bond is 2D band is coming because of two phonon process. That means each band will give, that means the nature of the band, how the band look like, whether it is sharp or very less intense, or it is broad, depends on that. You can get much information of about the graphene. Okay, so that means the G band is highly sensitive to the strains present in the or presence of any impurities. That means if your graphene, when you're preparing, if there are any strains present in your sample or if any impurities are there, so those things you can understand by seeing this nature of this G band. Similarly, this 2D band will show or predict how many graphene, because so when you are peeling out, right, this from graphite, there it is not compulsory that you will end up with single layer. Okay, it depends on process, you will end up with multi layers also. Okay, that means you can understand whether you got single layer or multi layer
So that can be understood by seeing the nature of this 2D band. So quickly see some results, like see. So you are having a single layer graphene as mentioned here. You have G band and a 2D band. So and you see when you are moving to multi-layer, what is happening? So your intensity of 2D band is decreasing. Okay, why it is decreasing? So because so when you are increasing, right, when you're increasing the multi layers, layer by layer graphene, so the movement of the vibrations of these carbon atoms will be decreased. So when it is decreasing, so you will have automatically a drop in the intensity of corresponding band. Even that is happening here also. Okay. Now coming to the next one, if any impurities, let us say we'll generally will not use graphene as a pure thing in the application point of view, because it is so it is not having a required band gap, because it's a it's a semi metal. Okay, so that's why what we do is we'll functionalize graphene with some molecules, like as a nitrogen functionalization or some chlorine functionalization. We do functionalization to improve the properties of graphene, to open the band gap of graphene. Okay, the best example here presented is functionalized graphene. Sorry, is functionalized graphene. So here you see the comparison between this pure and this one. When you are functionalizing the graphene, what you are bringing the impurities into the picture. When you are bringing the impurities, automatically there are two bands will come into picture. One is the D band, D dash, and you have D plus D. This generally will avoid this. That means main thing is a D band and D dash. Okay, so that means they are coming. If they are present in your sample Raman spectra means, so that means there is some impurities in your graphene. Okay, so that's why by taking the ratio of this ID and IG, okay, you will get information how pure your graphene is, and you can also control how much quantity of impurities are present there in from this ratio. Okay, so that's why you can control the how much functionalization you need to do for graphene. So another example is presented here is like you are seeing a graphene layer, okay, and you are having this one, right? So this is the image, and you are collected the data on top of the graphene, and another one is edge, right? That means you have collected the data at two different positions of the same graphene. At one place you are getting so similar to this one, and whereas in another case you are getting defects, or if any defects or impurities. That means it's quite common that when you have prepared graphene, the edges of the graphene will have definitely some functional groups. It's very difficult to remove them. So that can be understood by seeing this D bands, D and D dash bands. Okay. And the next class of materials, as I mentioned, transition metal dichalcogenides. So after graphene, uh, these materials are gaining a lot of attention. So the general formula is MX2, MO, and molybdenum, tungsten, titanium, niobium, and this one. So the main advantage is that these materials will have very good structure in such a way that you can tune the structure so that you can make them as metallic and you can make them as semi-metallic or semiconductor. Okay, that is not the case for graphene. Okay, so that's why though this electronic devices, those who are working on electronic devices, they started working on this transition metal dichalcogenides for those applications. Okay, and general formula is this, and if you take the typical Raman spectra of these materials, mainly it will show two Raman active modes. One is A1G, which is the vibrations of these chalcogenide atoms along the Z direction, and this is EG is along X direction. Okay, that means two bands it will show which are Raman active in Raman spectra. And here, this Lee et al. They prepared this transition metal dichalcogenides. Even these materials also layered materials, and you can use Scotch tape to peel out and get a single layer or multi-layer transition metal dichalcogenides. Okay, and when you're making that peeling, right, or exfoliation, there is a possibility that few places will have multi layers and few places will have single layers, and that is the case here. That means here you see here Raman imaging. That means Raman is not just used to get the spectra out of that. You can do imaging also with the help of Raman, and which will show clear contrast. So because of this contrast, you can get so at what place how many layers are present. Okay, and from that, and then you can focus your laser on that particular point and get the inform. I mean, collect the data from that, and so that you can have from the same sample you will have the data from single layer, data from multi layers, 2 layer, 3 layer, 4 layer, and if you present all the thing in a form. So that means if you take bulk TMDC, you will have this two peaks A1 E2G and A1G. Okay, and we'll fix that. We'll take that one as like a very fundamental parameter, the difference between these two values. Okay, and we'll take that as standard value and we'll compare that value with these values. That means after collecting the data immediately, you have to find the difference between the position of A1G and E2G. And if you take the difference and depends on that value, you can get this one. Okay. So that means with this also you can get layers. Okay. And it is not just knowing the layers, and we can also use to do the electron irradiation on graphene. Like you take graphene and you incident electron, and we are intentionally creating the defects to understand whether Raman spectroscopy is useful or not. And here you see clearly, so you are having the presence of other bands. Okay, D bands are present. That means when you are increasing the radiation time, so defects are increasing, and so that your D band is coming up. So you can find the ratio of ID to IG, and wherever you are having the maximum, right? So there you are having maximum defects. That means if you irradiate 50 seconds, you are having more defects. Okay, and then lattice strains also you can see. So like strains is nothing but if you have single layer, you will not have strain, right? So if you compare this one bulk MOS to, you are having again, you'll take the separation between the position of these two and you will compare with other results. If you see here multi-layer, I mean, nanoflakes prepared at different pH, and the strain partially released. That means if your data is closely matching with the bulk MOS2, it indicates that there are less strains present in your sample. Okay, if the difference between these two peaks is far from the difference between these two peaks of bulk, then there are a lot of strains present in your sample. Okay, so these strains again influence the position of electronic bands, and because of that you see the from bulk to when you are moving to nano, and you will see enhancement in the band gap. That means what is happening, it is not in visible range 1.3 electron volt, but when you are increasing the strains, it is going to visible range. That means you can tune the band gap and understand how much strain we can incorporate by understanding the Raman spectroscopy, and use those materials for the given applications. Okay, so this is all about understanding the nanomaterials or layered materials with the help of microscopic and spectroscopic techniques. So I hope I covered up to some extent. If anyone is having doubts or any questions or comments, please, the session is open for the questions. And I once again thank the organizers for giving me this opportunity. Thank you. Thank you so much.
Thank you, Dr. S.T. Ramanujan, for in detail information about various spectroscopic tools such as transmission electron microscopy and Raman spectroscopy on various materials. Now, the floor is open for the discussion. Students, come forward if you have any queries.
background. Like a Ramana said, I have a
Yes,
one
sir.
small doubt. I am not
Yeah,
the expert
tell me,
in
sir.
microscopy, but in the diagram that you showed, where the Raman spectra for 1 layer, 2 layer, 3 layer, and 4 layer, we
Yeah.
compared with bulk, right? So
Yes,
in
sir.
bulk, the intensity is less. For 1 layer, it is increased. 2 layer is further increased, and up to 4 layer, it is increased. It means that increasing the number of layers means intensity is
Yeah.
increased. But in bulk, it is become reverse, right? I
So
didn't
in
got the
five
point.
layers.
In bulk, it is less intensity compared to the 4 layers.
Yeah, bulk we have, and partially this one, not this one, right? Previous one. This one, right?
Yes, this one.
Yeah.
That yes.
So single layer, 2 layers, 3 layer, 4 layer. Yeah. So that means you see when you are moving from 1 layer to 2 layer, the separation between these two is decreasing, right? And from here 3 layer. Sorry, increasing,
Yes.
not decreasing, increasing.
Increasing. Intensity also is increasing. Am I right?
Yeah, intensity is okay, but the means the separation because the position is very important in this. Okay, so this here it is small, and compared to here it is little bit high, and this is little bit high, and it is little bit okay. So that means what is
Okay.
happening when you are increasing layers, okay, and it is approaching towards the bulk, right? Is it clear, sir?
Yes, sir. I got your point. You are comparing only the position and the intensities.
Yeah, say instead of like keeping the bulk here, if I keep bulk in top, so it might be more clear.
Okay, sir.
Yeah.
So can you show the TA image of atoms once? Our student wants to see the atoms, the image of atoms. Students, please have a look at the image of atom.
This slide,
Yes, sir. Can you see that?
this
The
is more
small
clear.
parts are atoms. Taken the image by transmission electron microscopy, you can see how the atoms are arranged regularly and periodically in a crystalline material. So this is a direct image taken from a transmission electron microscope instrument, which is costing about 10 crore rupees. Okay, this is the high-end version of your camera. You can see. Thank you, sir. Thank you once again.
Sir, S.T. Ramarao, sir, I have a small question, sir, small doubt.
Yeah, tell me, sir.
Sir, as you mentioned in the transmission electron microscope limitations and challenges,
Yes, sir.
while we are studying about thin materials,
Yeah.
compared to XRT, transmission electron microscopy studies would be very much preferred. So, in that note, can we take only transmission electron microscopy studies, excluding the X-ray? Is it advisable, sir, excluding the X-ray diffraction? Spend taking one more studies just
Yeah.
we take the transmission electron microscopy studies. Will it be
Hmm.
sufficient understanding the materials much better way?
Yeah.
Taking two studies, only one study, can we
So with the
get
TEM.
the information?
So the thing
Sir,
is, the PXRT, it will give the macroscopic view, sir, because when you are preparing a material, you will put some powder, right? Let us say, like some material you will put and you will collect the XRT from that. I mean, it will give the information about the whole sample. If any small misalignments that are present in your in the grains near grain boundaries, so that cannot be seen in the powder XRT. So where even that local deformations or the that misalignment of the grains are let the best example is like two graphene layers with some tilted angle. I think so. That is a famous paper given by Arindam Ghosh. So in from ISC, so two-layer graphene, so making some angle, magic angle. So they show the ferromagnetic result. So that means in order to show how much angle, that magic angle, so we need to have very powerful techniques which you cannot get from the XRD. we need obviously have some powerful microscopes to see that misalignments. In those cases, TM is more useful.
Okay, okay, okay. Thank you, sir, for your thank you for your enlightening talk, starting from the nanomaterials, how they are different from the bulk materials, understanding the nanomaterials using various microscopic tools such as transmission electron microscopy and the challenges, advantages, and further some spectroscopic tools like as induction coupled plasma atomic electron micro emission spectroscopy, Raman spectroscopy studies on various materials. Thank you, sir, for enlightening us with your very informative talk. Let us give a big round of applause for the nice talk.
Thank you, sir.
Thank
Thank
you,
you
sir,
so much.
once again. Thank you, sir.
Thank you, sir.
Sir, you can.
Yeah, thank you so much. Thank you all for joining with me.
Uh, so now we can go for the next session, next speaker. Sir, Narayana, sir, Dr. Narayana, sir, are you there, sir?
Yes, sir. Am I audible, sir?
Yes, sir. Yes, sir. Yes, sir.
Okay.
So, dear students, dear all, now we have the next session, next invited talk by Dr. Narayana Tota. He is from the Inspired faculty in NIT, Andhra Pradesh. Apart from that, visiting researcher, Department of Electronics and Materials Engineering at Australia National University, Australia. So let me give a brief introduction about the speaker. So he is presently a visiting researcher in Department of Electronics and Materials Engineering, Australia National University, Australia. Apart from that, National NIT, he is a inspired faculty. He completed his MSc from Sri Venkateswara University, Tirupati. Later, he did his PhD from Yogi Vemana University, Kadapa. He is a research associate. He did a research associate from 2016 to 18 in Institute of Technology, New Delhi. Later, inspired faculty in the solid state and structural chemistry unit, Indian Institute of Science, Bangalore. Later, he is inspired faculty in NIT Warangal, NIT Tadepalliguru. Next, he has various research interests in condensed matter physics, thin film photovoltaics, optoelectronics, inorganic semiconductors, quantum nanostructures, and 2D materials. He has a very hands-on experience and various experimental tools on XRD, UV visible, near infrared Raman spectroscopy studies, and probing various electronic characterization solar cells, Hall effect studies, and he has published 15 international journals in the reputed journals like Applied Surface Science, Solar Energy, Nano, and he has published one international book. He has attended and summer schools, two summer schools, and international conferences, six summer international conferences. He has international grants, inspired faculty from the Department of Science and Technology, India, of worth 1 lakh, 1 crore, 12 lakhs, and Jagadish Endowment Grant from Australia National University, one of the prestigious grant in the domain of nano science and technology from Australia National University, Australia, of worth $10,000, and international incoming mobility grant from the Belgium. And me. With this, I humbly invite Dr. Narayana Tota to start the session to deliver his talk.
Sir, many thanks for your kind introduction, sir. Many thanks.
Thank you, sir.
Is my screen is visible?
Yes, sir, absolutely.
Okay. Thanks for your kind introduction, sir. Good morning to all of you. Okay, this is my talk is on earth abundant photovoltaic observers and thin film solar cells. Mostly my work is on growth of area.
Interruption, sir.
Yes.
Sorry for the interruption, sir. Can you maximize the screen?
Okay, is it okay, sir, now?
Slide view. Yes, sir. Just press it. Yes, sir. Perfectly.
Okay.
Okay, sir. Thank you.
Okay, these are the what are the earth abundant different type of photovoltaic materials that are used in thin film solar cells. My talk is outline of the talk, mostly introduction to solar energy. What are the basic concepts where we have to focus on solar cells concepts and various current thin film solar cells that are running competing with the rest of the solar cells. And my work is based on kestrite thin film solar cells. This is the second generation solar cells. This is the introduction about energy. This is, as we know, energy is very important parameter for any society to grow economically and socially. This is for the just sake of introduction only. As we all know, the demand for energy is rapidly increasing than its supply. Currently, our demand is 15 terawatt energy we are in demand, and it is expected to go 30 terawatt level by 2050. Currently, we are receiving the energy by burning fossil fuels. See, this is the world energy electricity generation. You see, 65% of energy is we are using now from burning of fossil fuels. Burning of fossil fuels results to increase in greenhouse gases, acid rains, and degradation of public health, thereby total imbalance in the atmosphere. Now we already impacting its high temperature. We are observing its impact like high temperature in summer and greenhouse gases. These things, pollution. These are the adverse effect we are facing because of usage of fossil fuels. The immediate next step is we have to turn our focus on renewable energy sources. You see, this is the energy budget, overall energy usage by our whole planet. Generally, fossil fuels 68%. Nuclear is among the fossil fuels. Most of this 36% energy is by coal, burning of the coal. So this will radiates a lot of unwanted effects on us. And gas, oil is 3.1. Then the renewable energy portion is 26 percentage. Among the 26 percentage, hydro hydrocarbon, hydropower, wind power, and solar power. These are the alternative energy sources. Wind energy, hydropower, geothermal, and solar thermal. Among all these four alternative renewable energies, solar energy is very best option for us because it is abundant energy. We continuously receiving solar radiation from the sun. Generally, Earth receives 1 lakh terawatt per hour energy. So if you are able to utilize a fraction of this amount, this energy, this is sufficient for the total population energy need. So this is about the energy. So this is the solar spectrum that we are seeing. Generally, any body radiates energy. So if you take the surface temperature of the sun, it is above 5760 Kelvin. Because of this temperature, it radiates energy. It radiates in all directions and also Earth receives 10 power 15 watt radiation at the upper atmosphere. This is called extraterrestrial solar radiation. So this is 2000 watt per meter square. So when it meets the Earth atmosphere, some of the radiation will get reflected, some of the radiation will get absorbed. So while passing through the atmosphere before reaching the Earth, it undergoes several interactions, like it absorbs by the carbon dioxide, ozone, and water vapor. So this is called loss of radiation. And finally, after reaching the Earth's surface, we receive only 1000 watt per meter square. This is called AM 1.5. So at outside the atmosphere, we will get 2000. Because of these losses, reflection losses and absorption losses, these scattering losses, we receive 1000 watt per meter square solar radiation. This is the standard value that we are counting the while calculating solar cell efficiency. You can see this is the solar spectrum. This is the solar spectrum of this one. Most of the incident solar spectrum is at the visible range. See, this blue region, this yellow region, these are the bands which are due to absorption by the water molecules and CO2 and other scattering mechanisms. So this is the incident solar spectrum. This is among them 48.4% is visible solar radiation. If you are able to observe this visible solar radiation, that is solar cell, we have to develop a solar cells which absorb the most of the incident solar spectrum is visible light, which is about 380 to 720 nanometers. Then, so this is about the incident solar spectrum. So next one is, what is the basics of solar cell? A solar cell or photovoltaic cell is nothing but it is an electronic device which directly converts the sunlight into electricity. So we are receiving maximum UV light. So we have to first observe this light and then so these are the three series of steps that are there in generation of photovoltaic. First, when we observe the solar radiation, it creates the electron hole pairs. These electron hole pairs are separated by the junction electric field. Then these electrons will drive towards the ends of the solar cell. That is called light generated charge carriers. So there is a contact. Totally three steps. First, electrons holes will be created in the to observe the semiconductor. To observe the light, we need a semiconducting material. Generally, so different type of semiconductor. So you can see the three series of steps. First, light falls on the semiconductor, then electrons holes are created throughout the solar cell. Because of this is p-type material, this is n-type material. Because of diffusion, electric field will be generated. This electric field will drive the created electron hole pair towards the end contacts. One contact is this side, another contact is this side. Thereby, current will flow through external circuit. This is about the solar cell. Three processing steps that are involved in generation of photovoltaic, current and voltage. Three important parameters that we have to, while specifying the parameters of any solar cell. First, what is short circuit current, open circuit voltage, what is its fill factor, and efficiency. Not only efficiency, we have to see what is its fill factor, what is its short circuit current, and open circuit voltage. These are the four parameters that we have to take into account while evaluating the solar cell. And also, this quantum efficiency is also an important parameter to assess the solar cells. This gives how many photons are absorbed and how many are participating in the current. If generally, ideally, one photon should generate one electron pairs, and these electron holes are collected by the external contacts. If that is happen, that we call it as it has maximum efficiency 1 or 100% efficiency. You see this 10 gold line, this is 100% efficiency. That means whatever the photons that are absorbed, they created the electron hole pairs and they participated in the current generation. This is the ideal quantum efficiency, whereas this is ideal case only. Naturally, there will be many losses in the solar cell. That is recombination losses will be there and voltage losses will be there. So optical losses will be there. Because of these losses, this is the actual curve. So this is the cutoff wavelength for efficiency. If there is a too high wavelength also, that can pass through the Solar cell, if it is too low also, they are unable to generate the electron hole pairs. So these are the cutoff wavelengths. So solar cell is nothing but it is a type of PN junction. One is p-type PN junction. We have to consider one semiconductor that will give electron hole pairs. If there is a junction, this junction will separate the created electron hole pairs to the contact. So we have there are different type of solar cells based on the different junctions. One is homo junction, hetero junction, and semiconductor electrolyte junction. There are three main type of junctions that are using in the solar cells. If it is homo junction, that means if it is the same semiconductor material doped with a different type of material, different type of atoms, then we call it as a homo junction. It is an interface formed with the same base material is called homo junction. For example, a silicon is, we can dope it as a p-type material, same silicon can be doped as a n-type material. So here the base material is same. So that type of junctions we call it as a homo junction. And these type of solar cells we call it as a silicon solar cells or homo junction solar cell. Similarly, if you take a gallium arsenic, you can dope it as a p-type material, and same we can dope it as a n-type material. So this is called gallium arsenic homo junction solar cells. Then other one is heterojunction solar cells. These heterojunction solar cells are formed between two different semiconducting materials of different conductivity and different energy gaps. Say, for example, here we take it as a cadmium telluride solar cells. Cadmium telluride is a p-type material and CDS is a n-type material. These are two different materials with two different band gaps. So this type of materials we call it as a heterojunction solar cells. Whereas in this case, the host material is same material. That is we call it as a homo junction solar cells. Generally, there are two different band gaps. One small band gap material, we call it as absorber material, and high band gap, we call it as a window material. Main role of the absorber is which absorb the solar radiation and it creates the electron hole pairs. The other junction role is to separate the created electron hole pairs towards the contact. So the other material is large band gap material. This is called window material or buffer material, which transmits the most of the spectral solar radiation to the absorber. The third one is semiconductor electrolyte junction. This is not exactly a solar cell. This is like photoelectrochemical devices. Here the one junction is semiconductor, or the other junction is some solution. If you keep the solar cell, if we keep our material inside a solution, that is, there will be a junction formation between the semiconductor and the electrolyte. At this case also, there will be a charge transfer will takes place. This is called photoelectrochemical reactions. This is also, we call it as one of the energy devices. We call it as a semiconductor electrolyte junction. So these are the various type of solar cells, various generation solar cells. There are mainly broadly divided into three categories. One is first generation solar cells, second generation solar cells, and third generation solar cells. First generation solar cells are mainly silicon solar cells, and these are the silicon solar cells. Second generation solar cells are the thin film solar cells, and third generation solar cells are the new concept like perovskite solar cells, organic solar cells, polymer solar cells, or multi-junction solar cells. So these are the advanced concept, third generation solar cells. Whereas first generation solar cells are old in the sense well-studied solar cells, and they are very high efficiency and also cost is high. Mainly the reason is here the silicon solar cells, these are the vapor-based solar cells. So one concept we have to remember is, so for solar cells, what is absorption coefficient? Absorption coefficient depends on the inversely is proportional to thickness of the materials. Generally, silicon is an indirect band gap semiconductor, so it absorbs the less solar radiation. We need very thick material to absorb the incident solar spectrum. That's why this is called a vapor-based solar cell. It is about 200 micrometer. It is thick thick materials. So these are the polycrystalline materials and secondary. These are very studied material, well-established material. Currently, 80% of the market is dominated by silicon solar cell market. The problem with this material is, this is the indirect band gap material. It requires a lot of thick material to absorb the radiation. And also purification of the silicon is also very costly and laborious process. It involves too many steps, and there will be, if there are too many steps in, and also it is high temperature treatment. So we have to approach the Jacob process or the melt ground process to get the silicon wafers. So that's why this cost of these materials is high. Then the other thing is next materials are thin film materials. These are direct band gap semiconductor material. So his absorption coefficient is very high. It is silicon solar cell absorption is 10 power 2, whereas this thin film material, second generation material absorption coefficient is 10 power 5 per centimeters per cm square per cm, so that even very thin material is enough to absorb the most of the incident solar spectrum. There are different amorphous silicon, cadmium telluride, and CAGS. These are the different type of solar cells that are using in. And third generation as well, solar cells are recent solar cell, perovskite, small molecules, dicynthesized solar cells, or multi-junction solar cells. These are the solar. Mainly my talk today present on silicon solar cells, because these are very well material there, so we can get the maximum efficiency from these solar cells, and it requires low payback energy time. Low payback energy time in the sense, when we want to fabricate a device, we have to spend some energy. We have to heat it, and we have to process it. We have to take a lot of steps to be followed to produce a device. So we are investing some energy rather than money. We are investing some energy to fabricate a solar cells. Then payback time is with how much time it requires to give that energy back. That we call it as a payback energy. So for second generation thin film solar cells, their payback energy time is very less. So within 1 year, I think they will return whatever the energy we spent on it, they will return back to us. So, and also this is a thin film material, very small amount of material is required, and it is very cheap material. So it is extendable to very substrate. If the thin film is flexible, we can use it as a flexible solar cells also. So these are the various components. Generally, mostly we use the solar cell semiconducting material. The semiconductor starts from silicon. This is the group 4 element, silicon or germanium. So these are the progression of various semiconducting material. These possible compound semiconductor, they can be obtained by gradual substitution of elements from higher to lower groups. So you can see, take group 4 silicon, group 4 element. If you substitute or replace one group 4 element by two group 4 elements, 1 by 3, 1 by 5, then we call it as a 3-5 semiconductor. Similarly, if you take left side 2 steps to second group and right side 2 steps, that is called 2-6 semiconductor. Similarly, you can go progress like this. So these are the evaluation of various compound semiconductor that can be obtained used in solar cells. Actually, this is the absorbable material. Based on this absorbable material, the solar cell name is given. If it is the absorbable material is silicon, we call it as a silicon solar cell. If the absorbable material is amorphous silicon, we call it as a amorphous silicon solar cell. If the absorbable material is CAGS, copper, indium, gallium sulfide, then we call it as a CAGS solar cell. CDT. So based on this absorber name, they have given as a complete solar cell name. See, these are the 3 generation solar cells. These are the first generation solar cells, silicon solar cells. While as I mentioned previously, it is an indirect band gap material, so that it requires very thick material. You see, 500 micrometer wafer is required to absorb the solar radiation. So whereas in thin film solar cells, just it is the 2000 nanometers. That means 2 micrometer thickness film is enough to absorb the same radiation. So these are very thick solar cells. These are very thin solar cells. The other one is multi-generation. You can see here this is the solar spectrum. If you prepare a semiconducting material which absorb the suitable radiation, if you take the silicon or if you take the CAGS whose band gap is 1.5, so it can absorb only this part of spectrum. So if you want to observe this spectrum, we need one more material which absorbs this material. So if you have different materials, if you stack one over it, we can observe the most of the solar incident spectrum from starting from 500 to 1000. So this is the wide range. If you stack 3 different material, so each portion will observe each one certain spectrum of the solar radiation. You can see this is the top cell. it can absorb this part, and this is the medium cell. This can absorb this part. Like that, this total solar spectrum can be utilized for to conversion of light into electricity. This is called multi-junction solar cells. So these are the high efficient solar cells. Up to now, it has reached about 50 to something efficiency. When it is 4 devices are connected under concentrated light, it reached a 50 to something efficiency. So these are the different type of solar cell technologies currently we are in the system. So these are the various solar cells and their efficiencies. This is national NREL report that they will issue for every year. 5 years they will issue one report that is best solar cells research efficiencies. So this x-axis, this is solar cell this is the year, and this is the efficiency. We have different type of solar cells. You can see this is the maximum 47 up to this maximum 47. This is due to 6-junction solar cells, multicrystalline solar cells, which are 6-junction solar cells, or indium phosphide solar cells, where thin film solar cell efficiency is confined to at the 26%. CIG solar cells. This curve about. Here, one more I would like to mention. One thing is perovskite solar cells. Perovskite solar cells, the recent solar cells, they are very good. They emerged. They are competitive to very high efficiency solar cells, silicon solar cells, thin film solar cell in a short span of time. But their lifespan is very small, because we have to prepare the perovskites in glow box. Generally, if we say solar cell, whose lifetime should be in the at least 30 years, then only it can serve the purpose. Whereas the perovskite solar cells, still their lifetime is in the hours only. So that is still, I am not talking about currently it is out of discussion in my talk. But the efficiency wise, the number is very good number, attractive number, because silicon solar cell has taken almost 50 years to reach this high efficiency, whereas the perovskites has reached in 6 to 7 years. The active research, they reached to the same level, but the stability is still concern of this one. These are the different solar cells that are in the market. These are the solar. When it comes to thin film solar cells, this is the solar structure. You see, we need an absorber material to semiconducting material to absorb the solar radiation. So this we call it as a p-type material, because p-type material is a minority carrier devices, so that electrons are minority carriers in the p-type material, so their mobility is very high. So we have mostly people select as a p-type material as a absorber material. And for the junction formation, we have to take one more n-type material, and once junction is formed, one is top contact, other one is back contact and top contact. Because these are thin film materials, they cannot sustain there itself. They need one support. We call it as a substrate. This is called substrate. So these are the three important components. One is substrate, other one is back contact, next one is absorber material, that is p-type material, next one is buffer material, that is n-type material. Then it is TCOs, generally TCOs which transparent to light, so that it can transmit the most of the incident light to the absorber material, and contacts. So these are the four. When we are designing a solar cell, these 4 points we have to take in. So what type of absorber material is, what are the junction, and what are the top contacts and bottom contacts, and what is its substrate. Among them, substrate is an important thing, because it is the substrate which holds the remaining stacks. So different applications has different substrates. If you are dealing with very high temperature, the generally glass is used as a substrate. So if you are going more than 600 degrees temperature, glass is not suitable. We should think of other materials, other substrates. Whereas if you are processing your device at low temperature, some of the flexible solar cells, flexible materials also okay for using as a substrate. Next one is p-type material. These are the material characteristics for p-type material. The band gap should be 1.1 to 1.5, and absorption coefficient is in the range of 10^6, and it should have long minority carrier length, and its band offset should be aligned with the buffer and its bottom contact, and it should have low resistance, otherwise it will give the series resistance will be high, and it should have ohmic contact with the bottom contact. And the material availability should be more. It should be low cost, reproducible, and non-toxic. what are the main up to now is it is silicon solar cell, absorber is silicon, amorphous silicon, cadmium telluride, CaGS, and organic materials, various inorganic materials and perovskite materials are used as a absorber materials. Next one is buffer material. Buffer material is just to make a junction to the absorber. So it should their band diagram should be aligned each other. Thereby there will be less minimum recombination at the junction. So these are the different based on their absorber material. We have to select the its suitable N-type material. So for amorphous silicon, we have to select the amorphous hydrogen doped amorphous silicon. For CaGS, we have to select the cadmium telluride, zinc sulfide, zinc oxosulfide. These are the indium sulfide. These are the different buffer materials that are using in the thin film solar cell. Next one is TCO. TCO should be have low sheet resistance should be less than 10 ohm per square, and its transference will be more than 90. Generally, tin oxide, indium tin oxide, zinc oxide, these things are used as. Next one is contacts. One is front contact and back contact. Generally, for thin film solar cells, molybdenum will be used as a back contact, and front contact will be used as a silver, nickel. These things will be used as a front contact. Generally, sometimes efficiency depends on the contacts also. If you take the molybdenum, CaGS shown 22%. If you take the tungsten, it resulted 14 point. If you take the tantalum, it efficiency is 13%. Like that, some of the materials are good for contacts, where these titanium, manganese, chromium, these shown as very worst efficiencies, that is less than 2%, whereas these materials shown more than 10%. So in case of silicon solar cells, we use the silver, ZnOAg, AlAg, these things are the back contacts. So in coming to thin film solar cells, up to now, these are the two remarkable solar cells, that is CaGS solar cells and CDT. So they are currently in the market. CaGS solar cells shown 20.3% efficiency, whereas the cadmium telluride solar cells shown 21.5% efficiency. So the point is here, the efficiency wise, they are very good numbers, but here you can see the elements, indium, gallium. These are the rare element and expensive materials. Here, in case of second type of solar cell, cadmium telluride solar cell, this cadmium is a very toxic and tellurium are very toxic material. So for current users, it is okay. If you want to extend to the solar cell production to the multi-terawatt scale, then these availability and toxicity of the materials and the cost of these materials will come into picture. If you see, this is the various elements that are using in the solar cell and its abundance and cost. You can see CaGS, indium is very cost and its availability is low. Similarly, gallium is very high cost and its availability also very low. So it is the time to look for the new materials. Like if you replace the indium by zinc, see, you can take the zinc. Zinc is availability is very high, cost is also very less. If you replace the gallium by tin availability and cost both are very, availability is high and cost is also not too much high. So this is called copper, zinc, tin sulfide materials. So these are the properties of the material. This comes under the 1246 compound semiconducting material. It shows p-type conductivity. The band gap is 1.5, which is the suitable band gap to absorb the most of the incident solar spectrum, and absorption coefficient is more than 10 power 4. That means very thin material is enough to absorb the same amount as that of silicon is doing in 500 micrometer thick material. Materials are low cost, abundant, friendly. The structure is also stable structure, which is tetragonal stable structure. Up to now, it is started more than, I think, 2016. Active research is started 2010. It is initially started, and active research started from 2013 something. Now up to now, within 10 years, it's shown 13.6% conversion efficiency. So all these things encouraging us, we can believe it is a potential future material to the current existing thin film materials. So the material properties are very good, and also it's low cost and abundance is more. But you can see there is one challenge is there in this material. If you see the fundamentals, if you phase diagram of this material, this is the phase diagram of material. In this phase diagram, we have taken it as a sulfur is, we have 4 materials. One is copper, zinc, tin, sulfur, and sulfur is taken as a constant. So copper, zinc, tin, this is the phase diagram of this material. So this star indicates this material. So this is the very narrow region for existence of pure phase material. If you move away from this narrow region, there will be secondary phase formation in addition to CZTS, thin film solar cells. That's why you see. So our growth conditions should be very precise. We need a very precise control growth conditions to get the single phase material. If you have secondary phases, they are detrimental to solar cell. So those type of materials, if you use those type of materials which are secondary phases, impurity phases, that results very bad efficiency. So first we have to grow the pure materials. So this is very challenging material, because we can see in this whole area there's a very narrow region for existence of single phase. So we have to optimize our process parameter to be in this narrow region. And also there are various other elements are there: copper sulfide, copper zinc sulfide, zinc sulfide. So generally we use XRD to measure the impurity phases. If you see the XRD of CZTS, zinc sulfide, copper tin, their XRD is also overlapping. So we cannot find which the material is good or not just by XRD. We have to adopt different combination of characterization techniques to quantify to check the quality of this material. This is the major challenge that people are facing. The growth method. Growth is very precise control. We need very precise. So generally, we work on the CZTS, thin film solar cells. We have adopted two-step growth mechanism. First, we have deposited copper, zinc, tin sulfide by using sputtering method. For any thin film growth, there are two types of thin film growth methods. One is physical method and chemical method. In case of physical method, we are doing all our reactions in the vacuum environment, where chemicals reaction is different. We need some solutions or gas flow to form the material. Where we are using physical method, because we are doing in the vacuum, high vacuum, so that we can get quality, purity of the resulting material also very high. So we are using different type of techniques. There is sputtering is there, evaporation is there, pulse laser deposition is there, and many other methods are there to prepare these thin film materials. In this method, we adapted the sputtering method, where sputtering is nothing but just there are two cathode and anode is there. We apply high potential difference between them, and the gas in between gets ionized, thereby plasma will be created. So the material, when high energy ions hit the target material transforms from one substrate to target material in the plasma, so that there is a very less chance to get contamination of the material. So we have CAGS material. We use metallic targets: copper, zinc, tin, and this is the sputtering target. One is copper, zinc, tin. So we deposit by using sputtering method, and these metallic precursors will be used in tubular furnace. This is the two-zone tubular furnace. At one zone we use our sulfur power. At the other zone we keep our samples which are sputtered from the tri target sputtering. So we pass the carrier gas as argon, nitrogen. So this sulfur will be evaporated. And it moves to here, and it will react with this material and forms our required compound CZTS, thin film solar. There are two. One is we have done in the open atmosphere. This means the argon is continuously flowing through this tube, and the other one is we created the vacuum and inserted the argon and seal the tube. So this is the closed atmosphere. We approach two methods for synthesis of these materials. So mainly two-step method. This is for CAGS also. This is the successful method for high efficiency devices. The same methodology we adopted for CZTS, thin film solar cells also. So these are the growth kinetics. Generally, to get the optimized good quality films, we have to vary some parameters. What is the suitable temperature to get the single phase? What is the suitable annealing time to get the single phase? What pressure we need to keep it? How much sulfur we need to? So we have to vary the different process parameter to get the single phase material. So if we have varied the temperature also. At low temperatures, various bimetallic compound and sulfide metallic compounds are noticed. With increasing temperature, these bimetallic compounds are reacted with sulfur and dissociated into sulfide material. These sulfide material again reacted and form single phase CZTS thin film around 450 to 500. So again, if you increase the temperature more than 450 to 500, again the material will be decomposed into again its binaries. So what we believe is 450 to 500 is the suitable temperature to get it. And also we vary the time at low temperature, there will be sulfur deficiencies. With increasing of time, the sufficient sulfur is incorporated into the film. And one more critical point is here is we are using tin material. This is tin is very volatile element. Even it will try to evaporate at 200, 250. It will try to escape from the film. So we have used different type of stacking methodologies. So first we have, when the tin is top layer, there is a see the morphology is very bad morphology. We have almost film is peeled up. When we actually what we have used one copper as a capping layer, so that it protected the tin from the re-evaporation. And when the copper is capping layer, also there will be secondary phases. What happen is we divide the copper into two different thicknesses, and in between introduces. So generally copper diffusion coefficient is very high. When so it creates lot of vacancies. Through in that process, there will be proper mixing is done. And XRD usually, as previously mentioned, XRD is not suitable. It is XRD, only XRD is not sufficient to confirm the single phase of the material. So we move to Raman measurements. So these Raman measurements and also collected Raman mapping. This shows the single phase of the film. Different. We collect. This is the film. We collected top and bottom at 3 different points. Almost all the Raman spectra will show the same signal. That means the film is also uniformity. This is the Raman mapping conducted over these samples. So there is a possibility to other impurity elements to be present in the material. So we have conducted the XPS measurements. So thereby we calculate what is the composition. We have done EDS and XPS. Both EDS calculated the composition from EDS and XPS. Both shows almost similar results. So this XPS, copper is +1 state, zinc is +2 state, and tin is +4 state, and sulfur is in sulfide in compound form. So that case it's confirmed the single phase material. This is the preparation of single material. When it comes to device level, this is the substructure of this is glass, then back contact, then absorber material. This is the molybdenum is using as a back contact. The CZTS is our absorber material. So generally we are going 500 degrees temperature to get the quality material. When we are going to 500 degrees temperature, above that there is a material will be dissociated, so that this sulfur is reacting with the molybdenum. Thereby molybdenum sulfide is forming at the interface. This is the major. Many researchers reported this unwanted MOST is forming at the interface. So this interface will create the problems to the device. So what we tried is we used some graphene we deposited between the molybdenum and this absorber material. We deposited some graphene. We have taken the graphene flakes and DMO dissolved in DMO, so spin coated the graphene material. And then after that we processed the material synthesis. Then if we have done the cross-sectional temp previously without graphene, it is 100 nanometers MOS we are not able to notice. But after this graphene interlayer, the thickness of the graphene will come down to 20 nanometers. That means we are able to control the unwanted MOS to graphene between the interface of this material. This is the cross-sectional temp ADAF image of these things. So these are the Raman measurements and this is the Raman spectra for graphene and Raman spectra CZTS. This is the CZTS material. So generally 1.2 is the suitable band gap for solar cells. Here we got 1.5. So we tried to replace the sulfur with selenium. We incorporated selenium in a controlled manner to tune its optoelectronic properties. So with the introduction of selenium, the band gap reduces to 1.1. Generally 1.1 to 1.2 is the suitable optimum band gap for solar cell devices. So in place of, we slightly replaced the sulfur with selenium to get the suitable properties of this material. So finally molybdenum again the synthesis method is same. We have metallic precursor deposition, then sulfurization, selenization process. So these are the these are the characterization techniques. We have calculated the XRD and Raman spectra and calculated the beta plus. This is the band gap which is 1.05, and their composition is measured from the SEM. These are the morphology. See, at low temperature, this is CZTS has good grains, which actually we need large grains to get quality material. In the sense, the grain should be very at least 1 micrometer thick, micron size grains that are good for the solar cell application. Otherwise, if there is small grains, that means there will be recombination centers at a grain boundary. Again, actually, we try to replace the tin because tin is a volatile maintenance and its oxidation state is +2. It easily converted. It will go to +4 state. Thereby, +4 to +2 reduction in the tin element is there, and also 250. We are noticing the evaporation of tin from the sample. So we try to replace the tin with silicon. So we first deposited initially we partially replaced the tin by silicon. First we have prepared the copper zinc tin metal and silicon layer is sputtered. 5 minutes silicon layer sputtered. Then we have done 10 minutes silicon layer sputtered. Then these metallic layers were processed through the two-zone. 1 second, can you please? These devices are processed by using the RTA, rapid thermal annealing process. And these are their characterization, structural properties, Raman, and to confirm the phase. These are the band gaps. If without any silicon, it is 1.41. Then 10 nanometers, we have deposited the 10 minutes, not sorry, it is 10 minutes silicon deposition. There is a slight improvement in the band gap. And we can see here is we have done the cross-sectional TEM for this type of material. Generally, we need single growth, but while trying to replace the partial replacement of tin with silicon, we have seen the lamella growth because different type of layers we are noticing. Layer 1, layer 2, layer 3, layer 4, like we have noticed the layer structure. The top one is silicon, which contains completely copper zinc tin silicon. This bottom one is copper zinc tin sulfide. This is the silicon sulfide, this is tin sulfide. So silicon is unable to go into deep into the material. So we have this bilayer structure. Almost we have 3, 4, 5 layer structures. One is bottom layer is 500 nanometers, middle layer is 30 nanometers, the top layer is 1000 nanometers. Like that we have different nanometers. But this is the bottom layer has one band gap, the top layer has one band gap. So this type of materials has advantages and disadvantages, because if there is a varied band gap materials, we can utilize tandem materials. Tandem solar cell in the means each semiconductor has different band gap, so it can absorb the different solar spectrum. The same concept we can use it also, but when it comes to electron transport, when there is a different layers, there will be a recombination at the layer interface. That will be both advantage and disadvantage for these type of structures. So we use this for water splitting applications. So we use these type of materials for water splitting. So next time what we completely remove the tin and replace it with silicon. The band gap we observe is almost 2.7 high band gap material. These are not much suitable for solar cell application. So we used photoelectrochemical studies where we are inserting our semiconducting material into electrolyte. Then we share light on the light, then it will give the current. That is called water splitting application. We use this material for water splitting application. So this is the elemental conformation, oxidation state conformation. Then we have done the KPFM measurements also to study the surface potential of the material, how the surface potential at grain and grain boundary and all these things. So this work function at the grain and grain boundaries are found to be 4.91 and 4.93 electron volts respectively. It means grain boundary works surface potential is more compared to the grain surface potential. Generally, the belief is if there are grains, if there is a grains, that is grain boundary will be there. That grain boundary will act as a recombination center for the charge current. So what we've seen is we have seen some bit different results when at the grain boundary surface potential will be high when compared to grain interior. That means this grain boundary will be sometimes it is beneficial, which can create the electric field, thereby more effective charge separation of electrons and holes at the grain boundaries. So this is about KPFM results. So we use this type of we finish the device. We have taken the silicon and CDS is deposited, ZNO is deposited, and graphene oxide is deposited, because we are keeping our total device into electrolyte sodium sulfur Na2SO4 solution. So that will peel off our material. So we have used graphene oxide over here to protect the whole device, and kept it is generated the current. This is the current versus. So for CZTS it has shown less current. When we have done the junction, heterojunction, CZTS with CDS and ZNO, the current is increased. When still, if we increase the graphene layer, the durability is also increased. So why we have material, we optimize the material properties, and we try to increase the absorber quality, and we have done some modifications which are required for the solar cell properties. So next one is, first until now we focused on our CZTS only. Next one is, this is the P-type material. Next we have to deposit N-type material, that we have chosen as a CDS as a buffer layer. So we use,
Hello?
yes,
Can you hear me? Yes. Sir, I think you can conclude session, sir.
yes, okay.
Session. So you can conclude in 2-3 minutes.
Okay. Then we use the chemical bath deposition to make the N-type material. So this is we have prepared some precursors, a recipe to provide to get the CDS material. Then these aluminum doped ZNO were deposited by using sputtering. Then this is the cross-sectional image of the device. This is the bottom, this is the substrate and back contact, this is the surface CDS, and these are the cross-sectional image. And we have deposited the contacts by using aperture mask. So these cells were shown the actual, these are the efficiency curves, 1.6. And we have done some KPFM measurement to study the photovoltage distribution across the grain and grain boundary. The photovoltage is more at the grain boundary compared to the grain, which means that what we have actually would try to contact IBM people. They reported highest efficiency in type of solar cells. We bought some solar cells. We requested them some solar cells. They provide the solar cells, and we have done the photovoltage distribution measurements. Then if you measure the photovoltage distribution for single crystalline and polycrystalline material, but polycrystalline material generally, if it is a single crystal materials, there is no grain boundaries. Ideally it should give high efficiency. But actually in our case, we have noticed that polycrystalline materials show high efficiency when compared to the single crystalline materials. That means ground boundaries here playing a positive role rather than negative role. So these are the other materials that we have done. There are different losses. One is optical losses, electrical losses, and resistive losses in the solar cells. So this is about the second generation solar cells that we are focusing on the materials. Okay, thank you. This my talk is over. If any questions, I'm happy to answer it. Tirmal sir.
Thank you, sir. Thank you, Dr. Narayana Tota, sir, for enlightening us with your informative and exciting topic on the solar cells. Now the floor is open for the discussion. Audience, do you have any queries? Please post your questions.
Sir, your talk is so interesting.
Yes, thank you.
I have few questions.
Yes.
And first question is related to suppose I am taking paper structure.
Yes.
Containing two different compounds.
Yes.
So in that case, how do I choose some material is P type or N type?
Generally, in case of thin film solar cell, P-type material is the absorber material. Because it is a minority carrier device, so that electrons have high mobility. So in P-type, minority carriers are electrons. High electrons, we take P-type. Then we have to check its band alignment. How is there any trapping centers between? If there is we are creating a metallurgical junction between. Like in silicon solar cells, that is a homo junction. They are doing doping while growth, but we are physically depositing one layer over the other layer. In that case, we have to check the band alignment between these two materials without any loss. If there is any discontinuity at the band alignments, that will lead to negative effect. The electrons should transfer effectively through at the junction. We have to check the band element. First, we have to do the XPS and UPS measurements. Then we have to check the band elements. Is there any clips or bumps are there at the band interface? Those things we should take care into account.
Okay, sir. Overall, you are saying that means absorption coefficient and some band offsets are important at this point, right, sir?
Yes, band options are very important. Even we need Saki contacts also. Otherwise, if it is, there will be a drop at the voltage at the even at contacts rather than junction also.
Okay, sir. Another question is, suppose for this heterostructure, how this heterostructure with a band offset, the band offset means the electronic band discontinuity at the heterostructure. How this band offset can influence the VOC and ISC?
Yes, VOC generally is the quasi-Fermi level splitting, we call it as a open circuit voltage, VOC. If there is a band decrease, there is a quasi-Fermi level splitting will be very less. When there is a band offset will be more. So we try to nullify these band offsets. Somebody using some interlayers also, which sometimes it is very difficult to select the materials because the material property is very good, but this band alignment is not much as showing the favorable photovoltaic material. So we have to select some very thin buffer layer to make the offsets.
So, okay, overall, we have to reduce the band offsets, sir?
Yes, we have to reduce the band up. So that's why P-type, N-type silicon solar cells also PN junction. Generally, the structure is PIN structure. There is some intrinsic material will be there. Mainly, the idea to introduce the PIN structure is to offsets, to minimize these offsets, so that voltage drop will be less.
Okay, sir. And another question, precisely, if there are two band offsets, conduction band offset and valency band offsets,
Yes.
if suppose conduction band offset is a bit higher as compared to valency, so is it the device is good performance? It can show the good performance?
Generally, we start with Fermi leveling with Fermi level.
Right.
We start generally, we will leveling with Fermi level. First, we align the Fermi. Generally, they will align all Fermi level. From that, they calculate the conduction band offsets and valency band offsets.
Okay. In this heterostructure, there are interface and hetero interface as well. Surface electronic states are formed at the heterostructure in general. So this electronic, it means at the heterostructure.
Yes, sir.
Generally, surface and spectrostructure electronic states. Surface and interface electronic states. How these electronic states can influence this VOC and ISC particularly?
Actually, when there will be, if there is a lattice mismatch, that creates some potential fluctuations in the band gap.
That's right, sir. Suppose it's
sorry, sir, Ramesh, sir, we can sir will share these details. You can talk in detail with him. Any quick questions, one or two questions, as we are running out of time. One last question.
Yes, please.
Hello, good afternoon. Sir, I have a small doubt. In the beginning of the results, you have shown a band gap about 0.9 to 1.1 electron volt for solar cell applications.
Yes.
Whereas for water applications, it is in 2.5 to even 4.1.
For
water, you manage this?
Water splitting, actually, because that is because of reduction potential, oxidation potential of this water level.
My question is, how do you control the band gap? How do you
that's why we doped with this silicon. We doped this. We replaced the tin with silicon. That resulted 2.1 band gap, something around it. So that material actually we can use as a tandem structure, but ideally for primary solar cells it is not good. It is not suitable material. So That band gap is suitable for photoelectrochemical studies. So we use it for rather than solar cells, we use it for it the photoelectrochemical studies.
Thank you, sir. So I have a small personal question, sir,
Yes,
regarding this topic. In the solar cell, while we have the barrier potential will be the reason separation of the charge carriers, right, sir?
yes, yes, yes,
So
yes.
once photons are generated due to photons incident,
Uh,
that will create some build again they create an electric field which opposes the existing barrier field. So do we take any precautions to minimize this effect or any kind of?
Actually, that is the here the absorption coefficient will play a key role. If the thickness of material is too high, the charge carrier has to travel long distance to reach the contacts. So we have to adjust the thickness of material, which is just sufficient. If in case of say, thin film materials, if it is 2 micron thickness, that is enough to get the required voltage. If you increase the thickness, again it will be a disadvantage rather than advantage.
Okay, sir. Thank you, sir. Thank you very much, sir. So there are overwhelming responses from the audience.
Yes, sir.
So let us appreciate and thankful to the speaker with a big round of applause. He enlightened us with from the starting from energy and its role, solar cell and various types, uh, evolution of photovoltaic technologies, efficiencies of solar cells, and related experimental methodologies, structures, materials, and challenges. Thank you, sir. Thanks once again
So
for a nice
thank
talk.
you for the audience for their patience and thank you
So the
for
session,
providing me an opportunity to interact with you.
thank you, sir. Thank you once again. And the
Thank you.
session is completed on time. And now the next session will start at sharp 1:30. Thank you, audience. You can
Thank
leave
you.
and you again
Thank you.
join by 1:30. Thank you.
Thank you.